Hello students, in this video we have assignment 6.3. We'll be talking about self-induction, phenomena of self-induction, and one very important parameter of this phenomena, self-inductance, which is parameter of a coil or inductor. And we'll also see which are the physical parameters which affect the phenomena of self-induction and the parameter self-inductance. Consider a coil connected with a battery. Say this is a coil with n turns and I have connected it with battery. Now we know that as we pass current, say current I through the battery, we have magnetic field produced, and so can I say that there is flux linked with this coil? How much is the flux? Flux is uh, N B A, isn't it? What is N? Number of turns. B is magnetic induction, magnetic field produced by the current passing through the coil, and A is area. Now, what if I vary this voltage? What if I change the voltage? When you change the voltage, what you are doing is you are making change in the magnetic field or magnetic flux linked with the coil. And what if flux is changed? According to Faraday's law, EMF induced is equal to rate of change of flux, isn't it? It means that the coil will have induced EMF. So now you are talking about two potential differences. One is provided by the battery and other one induced inside the coil. And this phenomena is called self-induction. See, in case of induction, we have induced EMF, but most of the time, induction takes place because of some change in some external magnetic field. Whereas here, there is no external magnet, there is no external magnetic field. There is induction taking place because of something changing in the coil itself, and so it is called self-induction. The flux, this flux, these magnetic field lines are of coil, and change is also inside the coil, and then you have induced EMF inside the coil. So whenever current passing through any coil changes, the flux linked with the coil also changes, and hence you have induction taking place. This phenomenon is called self-induction, and the EMF is self-induced EMF. How do you find it? Obviously, we have only one way of finding out. It is given by Faraday. Epsilon is equal to minus d phi by dt. So, can I say that flux linked is directly proportional to current passing through it? Here, one thing you should be careful about is whenever you write phi, uh, be specific. If phi is flux linked with one term, you should multiply it with n to make sure you are talking about flux of coil and not flux of turn. N phi is total flux linked with the coil. Sometimes you might see capital phi, which itself is symbol of total flux, and in that case you don't need to multiply it with n. Now here n phi we consider as total flux linked with the coil, and then if I remove the proportionality, I get a constant L. What is L? L is called self-inductance of the coil. This coil is also referred to as inductor. Okay, and now if I make L subject of formula, what I get is, uh, let me write the equations again. So, total flux linked with the coil is proportional to current passing through it. Remove proportionality, and you have constant, that is self-inductance of the coil, make it subject of formula, and you have n phi by I. So how do I define L? Self-inductance of coil is total flux linked with the coil per unit current passing through it. Okay, that is one definition of the self-inductance. There is one more way of defining it. If I take n phi is equal to Li, and if I differentiate both sides, I get d phi by dt is equal to L di by dt. And then I can say that uh, it is minus n epsilon, sorry, it is minus epsilon is equal to L di by dt, because we know that according to Faraday's law, rate of change in flux is self-induced EMF, and this negative sign is consequence of Lenz's law. So now if I make L subject of formula, what do I get? L is equal to epsilon upon di by dt. What is epsilon? Self-induced EMF. What is di by dt? It is rate of change in current passing through the coil. So according to this, if I again try to define the self-induced EMF, sorry, self-inductance, then I can say that self-inductance of a coil is equal to self-induced EMF in the coil per unit rate of change in current passing through the coil. So that is the second definition of self-inductance of a coil. Which are the parameters affecting L? Obviously, as we are talking about phi, the shape and size of the coil, okay, that is very important parameter. Then number of turns of the coil, and lastly, shape and size, sorry, shape and size of coil, then number of turns of the coil, and medium inside the coil or inductor. So if you have one coil, say with air inside, and then you change the voltage, you will have some induced EMF. But then if you put some iron core, say if you have introduced some soft iron inside this, if you put some iron bar inside it, and then again if you repeat the experiment, you will see that self-induced EMF will change. So what you have inside the coil is also important parameter. Okay, so this is the phenomena of self-induction. And what is self-induction? A phenomena in which when current passing through a coil changes, flux linked with the coil also change, and this phenomenon is self-induction. Because of change in flux, there is self-induced EMF. Then you have two definitions of L, self-inductance. This is first definition, flux linked per unit current. This is second definition, self-induced EMF per unit rate of change in current. And lastly, which are the parameters? Mainly three: shape and size of the coil, uh, then second one is number of turns of the coil, and medium. Now apart from this, I would like to explain one more thing. Consider that in a coil you are increasing the voltage. Say you are going from 0 volt to 1 volt to 2 volt to 3 volt, say up to 5 volt. Okay, we are increasing the voltage. What will happen to the flux? As you increase the voltage, you are increasing flux. Now, as you are increasing flux, according to Lenz's law, the tendency of the coil is to resist or oppose the change. So in that case, the induced EMF of the coil will be in such a way that it opposes your action, that is increment in voltage, and then the induced EMF will be like this. The coil will behave as if it is battery with positive terminal facing external positive, negative facing external negative. Then only it can oppose. But then after reaching 5 volts, suppose now if you are going from 5 volt to 0 volt, okay, again you are changing voltage, but now what is the condition? Now you are going from 5 to 4 to 3 to 2 to 1 to 0. You are trying to decrease the voltage. So at that time, what is the tendency of the coil, or what is the nature of induced EMF? So as you decrease the voltage, what you are doing, you are decreasing flux, and then what is the tendency of the coil? Not to let you decrease the flux. And in that case, the induced EMF will be in such a way that the coil behaves like battery with negative facing positive, positive of induced battery corresponding to negative outside. So don't assume that the induced EMF is always opposing the external battery. No, it is not opposing the external battery. It is opposing the change. If you are increasing voltage, the induced EMF will not let you increase the voltage. So it will produce current in opposite direction. If you are decreasing external current, then the induced battery will try to compensate with it. Okay, by producing the induced voltage in helping condition. So this is very crucial point which you should not forget when you are solving problems of self-induced EMF. So that is all for now. Thank you.